is known as transformer regulation. So in this module, we have basically learned about the the performance of the transformer, how they are modeled by the different types of uh, the no load condition, and gradually we understood the transformer principle, how the different circuit parameters come into the play, and how the magnetization takes place, how it is modeled in the form of a circuit, and then we saw about the transformer equivalent circuit, and then about the notion of approximate equivalent circuit to make the computations simpler. So gradually, we what is actually required is there are thousands of transformers used in electrical power systems. We cannot there cannot be an electrical power system without transformer. Even in our household appliances, there are a lot of transformers inside the appliances. So it is also required to measure the performance of the transformer. Okay, how the transformer is performing. So one of the concepts for measuring the performance of the transformer is known as the transformer regulation. So the voltage regulation of a transformer, it is basically defined as the ratio of the change in magnitude of the secondary voltage when full load at a specific power factor is thrown off, with the primary voltage and frequency held constant. So what is the meaning of thrown off? That means the transformer with a fixed primary voltage and frequency, it was supplying to some load. Okay, so there was a secondary voltage V2, and it was supplying full load at a specific power factor. Now suddenly, if that load is removed, okay, so if the load is removed, so then their output at the output of the transformer, basically it will be the no load voltage. It will be the open circuit voltage. So what will be the difference in that voltage across the secondary terminals when the load is thrown off with respect to the full load voltage is known as the transformer regulation. So we will define it mathematically. So the percentage regulation, it is expressed in percentage, is defined is the change in voltage magnitude with load, and divided by the rated full load secondary voltage magnitude into 100%. Obviously with respect to percent, so this is how it is defined. There is the percentage regulation, change in voltage magnitude with load divided by the rated full load secondary voltage by 100 into 100. So so mathematically it is like this, that V2, the terminal, the secondary voltage at no load, minus the secondary voltage at full load, divided by the secondary voltage at full load into 100. So that is the meaning. The numerator is basically the difference between the no load voltage and the full load voltage, and the denominator is the full load voltage. So numerator is basically the difference divided by the full load voltage, and obviously at the secondary, the 2 stands for the secondary terminal. So this you are already aware of it. So this is known as the transformer regulation. So how will it happen? The practicing engineers, there are a lot of engineers are there to run the power grid throughout the country. There are engineers. So without the services of these engineers, we don't get uninterrupted power. So because as soon as there is a power interruption, we lodge a complaint. We call up some call center number, or some place where the engineers are located, and they also they are all they are they rush there to restore the services. So these engineers, they basically have to maintain a certain voltage. We all want a certain voltage at our home. Without that voltage, below a certain voltage, the electrical appliances will not run, or it may even result in a malfunction of the appliances. So the practicing engineers, they use regulation to maintain the voltage within specific limits at the consumer terminals by regulating the primary voltage. So that means as soon as some load is thrown off, and loads also keep on fluctuating. We off and on, we increase we switch on the devices, switch off the devices, but the supplier or the engineers have to basically maintain the voltage at the customer's doorstep. So for doing that, what they do is they regulate the primary voltage. So this is basically the equivalent or approximate equivalent circuit of a transformer we have seen. That the R equivalent, you know what is R equivalent, you know X equivalent. So that is the transformer and it is supplying to some load. And V1 is the supply voltage, primary supply voltage, and V2 is basically the load, the voltage at the customer terminals, which is basically the load terminals. So this equation is very simple. V1 equal to, if you apply the normal KVL, V1 equal to, the voltage drop along the circuit, okay, along the inside the transformer REQ and XQ plus the voltage at the load. Simple. So see, this is a simple single phase transformer and one single phase load. So this is the equation. V1 equal to V2 plus REQ plus JAQ I1. So R and J, why R and X? They basically represent the impedance. And so this is the relation. And so V1 minus V2, so that is the difference, which is equal to R plus J XEQ into I1. Now this I1 is basically the full load current. That is there is a load current which the transformer can deliver maximum. Okay, so that is basically the full load current. Sometimes you can even run the transformer at less than full load current. It can even, transformers are designed, so that it can even partially go above the full load current also. Okay. So, but full load current is the rated current which you can find out from the nameplate readings. So this voltage equation, we all are related to the phasor diagrams, can be related to the phasors. So V2 is the terminal voltage across the load which we have taken along the reference. And suppose the load is of, most of the loads in the power system are basically lagging loads. Okay, so we all know that, suppose assuming that the load is to be lagging, then this current I1 will lag this voltage V2 but by an angle theta, depending upon the power factor angle of the load. So it is basically the power factor angle of the load as well as REQ and XEQ all jointly will lead to this current. Now this V2, so how to get this V1? So to get V1, you have to basically do the phasor addition of V2 plus REQ plus J XEQ I1. So I1 REQ, where is it? I1 REQ. Where will be I1 REQ?
So along V2.
Along?
I1.
Along I1.
It will be in parallel with I1. It is the resistive component. So it will be added at the end of V2. Okay, so by this what we get is V2 plus I1 REQ. And J XEQ or I1, where will it be? It will be?
Say perpendicular.
90 degree below I1.
90 degree below. So it will be 90 degree ahead of I1.
Above.
Okay,
Yes.
so it will be somewhere like here. Okay. So this one, so V2 plus I1 REQ plus J I1 XEQ, if you add this, once you complete this phasor addition, it will actually lead to your V1. Okay, so it will actually lead to your V1. So this is how the phasors get developed. So we have to start from the load, because you don't have any control over the load. At the customer end, the customer wants the voltage at a particular level, and obviously depending upon the the usage of the customer, the angle between that voltage and the current will be determined. So that current has to be supplied by the supplier. Okay, so that same current has to pass through REQ, XEQ. So that will actually add up to the V2 in this way of phasor addition, and ultimately it will generate the terminal voltage V1. So you see, to maintain a certain V2, only the V1 has to be controlled, and the power supply company has only control over the V1 because they are operating the generators. The power supply component cannot control I1 because that is all upon the customer's wish, the way the customers are using the power or what type of appliances they are using. So the customer will dictate by drawing the I1 and at the drawing the power at a particular theta, and the supplier has to basically provide that by controlling V1 and also maintaining a certain V2 across the customer terminals. Okay, suppose you are buying power from, suppose those of you are in Kolkata, suppose buying power from CESC, Kolkata Electric Supply Corporation. Okay, you will not be happy if your voltage at your home is at below a certain level, and because if it is a certain level, some devices may not operate. Okay, some devices may even get damaged at a certain below a certain level. So the customer has to provide the supplier has to provide that. So this V1 ultimately makes a certain angle delta with V2. Yes.
Sir, sometimes in Kolkata, a lot of voltage fluctuations occur. Like fans go slow. So why is that? Is it because of this? The load.
So is it because of this or the generator problem? I also want to.
Yes, sir. Yes, sir.
In which area of Kolkata you are staying?
Sir, I'm in Keshtapur. A lot of voltage fluctuations occur during Durga Puja and also Kalboshaki the times.
So, there are many factors here. I can just tell from my own experience because before being a professor of IIT Kharagpur, I was an engineer of CSC only. I worked there for 3 years. So, during, as you told, during this Durga Puja or during the festivals, there will be lot of temporary supplies, lot of temporary, even there may be some unauthorized usage of voltage taking place. Okay, so so the V1, the supplier, they cannot give an infinite amount of voltage. Then what will actually it will lead to the V2 that is at the customer end will keep on falling. Okay, if you draw more and more current, if your I1 is increasing, and the power supply company has some calculations, but if more than that is being drawn, then what will it will basically lead to a droppage of V2 because beyond a certain limit the V1 cannot also be operated. Okay, so does it answer your question?
Yes, sir, got it.
Okay, so so this is how the voltages are related, the customer end voltage V2 and the supplier voltage V1, and at the end the voltage V1 and V2, they have a small angle delta between them. Okay, so we have to, from here we will derive what is called the transformer regulation. So you just remember this formula of this transformer regulation, that is V2 no load minus the V2 full load by V2 full load into 100. So we will basically work on this phasor diagram now. So when the load is thrown off, suppose the load is thrown off, means suddenly due to, as someone told, during some storm or something, suddenly some wire gets snapped. Okay, if the wire gets snapped at the load end, then what will actually eventually result in I2 becomes 0. Okay, so if the I2 becomes 0, what happens to V2? If I2 becomes 0, what happens to V2? The wire gets snapped at the load end. Some big tree has fallen and the wire has got snapped. What will happen to V2?
So it becomes 0.
V2 will become 0. The wire has
So V1.
So it will become V1.
Equals to V1.
It will become equal to V1 because it is just become an open circuit transformer. Because from the supply it is still there. Is still there, but if it has snapped here at the load end, then it will just, the whole voltage will be available. And it was a very common phenomenon earlier, even inside IIT Kharagpur. We have heard from our senior professors, because in IIT Kharagpur there are a lot of big trees, and because after any storm, all these trees used to fall, and if they fell over some power line, the wires used to snap, and there were occasions where for days there was no power in the hostels and all. We have also heard about these stories from the senior professors, but nowadays in IIT, when you come here, that thing will not happen because now most of the wiring is underground. Okay, so even if the trees fall, no major disruption takes place. So when the load is thrown off, that is when the full load current suddenly it becomes zero. This I1 equal to 0. So your V1, which is equal to the V2 no load. So the V2 no load basically becomes equal to the supply voltage because of the open circuit condition. So we basically want this V2 no load, this V2 no load minus V2 full load by V2 full load to calculate the transformer regulation. So we have this circuit. Okay, so we have this circuit from our earlier condition. So this is basically the phasor diagram for the lagging power factor. When you have a lagging power factor, we have assumed that the I1 is lagging V2, and we have arrived at this phasor diagram. Now, this REQ and SQ are small in magnitude as compared to V1 and V2. The value of REQ and XEQ, though I have shown it in the magnified form to explain the phenomenon of regulation, they are actually very small in magnitude compared to the actual values of V1 and V2. Someone, you may mute yourself. Okay, so the values are basically small as compared to V1 and V2. So, and the delta, that is the angle between V1 and V2, is actually very small, and it is only in a few degrees. Though I have shown it in a magnified form for better explanation. So it is basically in a very few degrees. So the objective is actually to find out the difference between the V2 no load minus the V2 full load divided by V2 full load. Okay. So what we do is we draw some, do some plane geometry, and so if you draw this perpendicular to this, so this angle is theta. If you draw this perpendicular to this angle is theta because this is theta. Okay, and this is 90 degrees. So these two are vertically opposite, and ultimately this angle is also theta. Okay.
Yes, sir.
Yes, sir.
Okay, now we draw some more, to find out this difference, and we give some names. This is the origin O. This point we name as A. This point we name as B, and this point we name as C. And ultimately, our work is, to find out the, to find out this OC is nearly equal to OB. Okay, why is it OC is very nearly equal to OB? Because OC is basically V1, which is equal to the V2 no load condition. Okay, and OC is very nearly equal to OB. Why?
Delta is very small.
Delta is very small.
Delta is very small.
It is in few degrees. Okay, 3 degree, 4 degree, and so on. So, all of you are experts in trigonometry. So this OC is nearly equal to OB. So what we actually need is, so this V1 is basically then becomes equal to OB. So once V1 is nearly is equal to OB, we basically need the difference between V1 and V2 to find to compute the numerator, then divided by the V2. So V1 minus V2 is basically OB minus OA, and so this is ultimately equal to AB. So this length of AB is basically the difference of the expression in the regulator, in the regulation equation. Okay, the numerator of the regulation equation, that is V2 no load minus V2 full load. So that is V1 minus V2, and ultimately we have to compute this. So this AB is again of two parts. Okay, so if this AB, if you compute this, okay, so from A to this tip, so the component of this, which is along the horizontal, and the component of I1 x cube, that is along the horizontal. So these two components will add up to generate AB. So basically these two components will if you can find out, that will become equal to the length of AB. So what is the first component?
I1 R equivalent cos theta.
I1 R equal cos theta. Simple geometry, trigonometry, all of you have know this. Similarly, what is the next component?
I1 x equivalent sin theta.
I1 x equivalent sin theta.
Yes.
Okay, so these two added is basically equal to AB equal to the numerator of the regulation equation. So this you have got the AB. So the expression for the voltage regulation, which is V1 minus V2 by V2, this was the voltage regulation. So it comes down to, so you can replace this expression in the numerator, so which is I1 Req cos theta plus Xeq sin theta by V2. Okay, so I1 Req cos theta plus Xeq sin theta by V2. So this is actually a very important formula which you will be required, even to solve problems in relative transformer. If you are asked to find out the regulation, basically you need to compute Req cos theta plus Xeq sin theta by V2, and the numerator is multiplied by I1. So this is the expression of regulation, a formula of regulation, and this formula is again valid for lagging power factor. See, for theta lagging, this is the formula. You can find out for theta leading what will be the formula. So this comes from the phasor diagram for a lagging power factor. That is, voltage regulation is equal to I1 Req cos theta plus Xeq sin theta by V2. Okay.
Yes, sir.
Sir,
Similarly,
sir, is this voltage regulation a constant quantity, or shouldn't it depend on the load, because theta depends on the load and V2 also depends on the load? So is it a constant quantity? Like, can we define it for a fixed transformer, for example?
is your load fixed?
No, it isn't.
So then will it be fixed?
No, it shouldn't be. That's what I'm saying.
Your load is varying. For the power supply company, they don't know what is the load. They have some, seasonal picture of the load. They don't have, yearly picture of the load, but the load is varying because the customer behavior is varying. Okay, so the customer behavior, so this theta, I1 and all are varying. The values of the current, the angle, all are varying. So your regulation will also keep on varying.
Okay, sir.
And again, this is only for the lagging power factor. If you have a leading power factor, it will be, equation will be something different. So can you find out what the leading power factor, what will be the voltage regulation formula?
Sir, replace theta with minus theta.
Yeah, so ultimately what will happen?
Minus
x
Xeq.
eq sin
Minus sin x equivalent sin theta.
The plus will become minus. You can also find out from, by drawing the phasor diagram. So you can also try to find out by drawing the. So for lagging power factor, this is plus in the numerator, but for a leading, this will be minus. So if you draw the phasor diagram for a lagging load, you see this is the phasor diagram of a lagging load. So V2, the current I1 is leading the voltage by an angle theta. So if you keep on drawing, I1 Req will be parallel to this I1, and then J1 Xeq will be perpendicular. So if you add these phasor additions, V1 plus I1 Req plus J1 Xeq, so then this will be your V1. This will be your V1. So following the same approach, you can show that the voltage regulation or the percentage voltage regulation. Obviously, I have not written that percent into 100. So there is a 100 also into 100. So the percent voltage regulation is I1 Req cos theta minus Jeq sin theta by V2. So this voltage regulation is often represented in per unit rather than in percent. So this is again another new terminology in electrical engineering, which is the per unit. the concept of per unit, the values may be very, very high. Okay, so the per unit is some sort of normalizing the values. Okay, and representing the value. So rather than representing in percent, the values or the voltage regulation is also expressed in parts per unit. So how the per unit is defined? So per unit is defined as the quantity, is the ratio of the actual value to the base value or reference value of the quantity. Okay, so the way, many of these calculations are made, some sort of a normalization. Okay, the per unit quantity of a value of a quantity is the ratio of the actual value to the base or a reference value of the quantity. So, like if say your voltage V2 and the current I1 are taken as the base voltage and base current respectively. If a certain value of the voltage and if a certain value of the current are taken as the base voltage and base current respectively, then the base value of impedance is given by V2 by I1. If we are assume a certain V2 as the base voltage and we assume a certain current as the base current, then with respect to that base voltage and base current, base value of the impedance is basically V2 by I1. So R per unit, so R per unit is nothing but R actual by R Z base. R per unit is equal to R actual by Z base. So if you multiply both the numerator and denominator by I1, so it is R actual into I1 by V2. So I1 and V2 are basically the base quantities for the current and voltage. So that is how the R per unit is expressed. Okay, so you have the actual value of resistance. So actual value of the resistance multiplied by I1 divided by V2, it is the per unit value of the resistance. You see, what will be the dimension of this per unit?
Dimensionless.
Dimensionless. Okay.
So there is no
So
dimension.
this per unit value of resistance will be the dimension. So this is how per unit values are calculated. Similarly, X per unit is X actual by Z base equal to X actual into I1 by V2. Again, you see the numerator dimension is also volts. The denominator dimension is also volts. So per unit value is actually a dimensionless quantity. So from here you can get that the per unit regulation. You see the per unit regulation, sometimes you will find it is written in the per unit regulation is equal to RPU cos theta plus minus XPU sin theta. PU means the per unit value of the resistance, per unit value of the reactance. So this is known as the per unit regulation. So this plus minus thing, plus is when the load is a lagging load and it will become minus when the load is a leading load. That is why this plus minus.
Sir, per unit regulation and regulation in percent both are different.
Both are?
Different things.
Both are different things.
Yes, sir. I'm asking that both are different or same.
It is the different ways of expressing the regulation. We have defined with respect to the percentage, but as I am telling that in per unit is another way of representing and the quantities.
Okay, sir.
Instead of the percentage. So
Z base is a load plus Z equivalent or only load?
for lagging power factor, so you can see for a particular value of theta, even the regulation value may be negative also. If your XPU sin theta value is greater than RPU cos theta for some leading load, then the regulation value may also be negative. Okay. Can you hear me?
Yes,
Yes,
you got disconnected
Yes,
for
sir.
2-3 seconds.
Yeah, but then again it came back. Yeah. So this is how the concept. This is the concept of regulation is. Okay. So for a given load, you may be you may have to compute the value of regulation. If you calculate in terms of percentage, you will have to use this formula, percent voltage regulation, or you can even give it in per unit form. Okay. Okay.
Yes, sir.
So what is the significance of Z base?
Z base is the base value of the impedance, because as soon as we assume a base value of voltage and a base value of current, the base value of the impedance gets defined because they are related.
Okay, sir.
So with the base value of voltage and base value of current, if somewhere so there is some requirement, the base value of power gets defined because they are again related to power.
Excuse me, sir. Sir, in the Z base, are V2 and I1 rated values or the value at that instant?
They are some fixed values. Some value we will assume.
Okay, sir.
For V2, and they are not varying with time. They are some fixed values. So suppose you have a problem here that you are given a 4 kVA, 200, 400 volts, 50 hertz single phase transformer, which gave the following test results. You know what is the meaning of test results? We have done the no load test and the short circuit test in the previous class. So the low voltage data for no load is given. That is, you do the low voltage test or the open circuit test by applying the low voltage, by energizing the low voltage side. And we got the values of 200 volts, 0.7 amperes and 60 watts. Similarly, the high voltage data for the short circuit test is given by this. So the question is, calculate the magnetizing current and the component corresponding to iron loss at normal voltage and frequency, the efficiency on full load and unity power factor, the secondary voltage and full load at power factors. The secondary voltage you are asked at full load, but there can be different power factors at the secondary. It could be unity, it could be 0.8 lag, it could be 0.8 lead. Okay, so try to do this problem. So tomorrow we will have more problems in the tutorial, but we will also have some problems while we discuss different topics.
So the tutorial has to be submitted when can you say?
So at least you will get 1 week time. From tomorrow it will start, and then it will get 6-7 days time. We'll announce in the tutorial. So the no load test data is basically this: V1 equal to 200 volts, PC, that is the reading of the watt meter, is 60 watts. The I0, the no load current, is basically a 0.7 amperes. So you know what you can get out of this. You can find out the parallel branch parameter. So you get Y0 or YC, or you could also find out ZC. That is I0 by V1. Similarly, what you can find out? What else you can find out?
So resistance, sir.
Yeah.
Resistance.
So in this case, it will be GC, the conductance. So GC is equal to PC by V1 square. So it is V square by R. So it is V square GC is the power. So it is GC equal to PC by V1 square, which you can find out. PC is 60 and V1 200 square. You can find out the value of GC. Obviously, since we have found conductance, you should use the correct unit. So once you get YC and GC, you can find out the BM. Okay, so it is YC square minus GC square So this you get from the no load test data. And you can find out the the magnetizing branch currents and all. Because that was the first question, the magnetizing current and the component corresponding to iron loss and normal voltage and frequency. Similarly, from the short circuit test data, which is basically conducted on the high voltage side, the short circuit voltage is 9 volts, the short circuit current is 6 amperes, and the short circuit data. From the short circuit data, what will you get?
So Z value we can get. Z equivalent.
R1 equivalent and X equivalent.
So R equivalent and X equivalent. So you find out what is R equivalent.
V square by P.
Yeah. So and you will get the Z equivalent from this V by I.
Yes,
So
sir.
from here you can find out the X equivalent. So once we have found out this, once we have found out these circuit parameters, okay, then what is required is to find out the other things. The efficiency on full load and unity power factor, the secondary terminal voltage. So once we have found this, basically we can draw the what? The equivalent circuit. Once we have got this, because we have found out the equivalent circuit, you can draw the equivalent circuit. Okay. So for drawing the equivalent circuit, what is required? The short circuit test data is referred to the high voltage side. You see the short circuit test is done on the high voltage side, while the open circuit test is done on the low voltage side. So you have to basically refer them to one side first. So if we refer everything to the low voltage side, then basically you have to nothing to do on the no load test data. But you will have to transfer the high voltage side parameters that are determined using the short circuit test to the low voltage side. So from the low voltage side to the high voltage side, so this is basically the turns ratio. The low voltage side, the low voltage is 200 by and the high voltage is 400. So the A is basically 200 by 400, which is equal to 0.5. So the resistance, that is the series resistance, referred to the low voltage side, that is Req referred to the low voltage side. So Req referred to the low voltage side is nothing but Req dash equal to A square R. R value was 0.6, but that 0.6 was determined with respect to the high voltage side because the short circuit test is done from the high voltage side. So either you have to transfer the high voltage side parameters with respect to the low voltage side or the low voltage side parameters with respect to the high voltage side. So we are basically transferring the high voltage side parameters with respect to the low voltage. So resistance referred to the low voltage side Req dash equal to A square R equal to 0.15 ohms. Similarly, the reactance referred to the low voltage side Req dash equal to A square X equal to 0.25, 1.375 equal to 0.344 ohms. Okay, so once we have this, you can now complete the equivalent circuit of the transformer. So the equivalent circuit of the transformer, so all of you draw the equivalent circuit of the transformer. What will be on the left hand side?
So 200 volt.
The low voltage. Okay, so because we are drawing with respect to the low voltage side. Okay, so So this is basically the equivalent circuit of the transformer. On the left side is 200 volts. Then you have this parallel branch, which is exactly the same that has been found out from the open circuit test. But this is basically the parameters which have been now referred back to the low voltage side, which we just found out. These values. So these are the resistance and reactances found out by referring to the low voltage side. Huh?
So is it necessary to show the resistance value in conductance form or susceptance form?
No. You can show it by resistance form also.
Yeah, okay. So
in fact, it may be convenient to do by
so resistance and
resistance forms. Yeah.
Yes, sir.
So this example I found somewhere. So from there I'm directly taking, but it is in many other places you will find that it is. Because ultimately it is the same parameter. Okay. So whether you call that resistance by resistance ohm or mho, it is basically the same element being referred. Okay. Similarly the coil, similarly the reactance. So now the next part of the question is output on full load at unity power factor. So the efficiency at full load at unity power factor. So the output at full load at unity power factor. What is the output at full load at unity power factor? How did I get this? 4000 watts. Can anybody tell? Output at full load at unity power factor, I suddenly wrote 4000 watts.
4 kVA is given. And if cos phi is 1, then 4 kVA becomes 4000
Yes, because the transformer is given rated capacity is 4 kVA or 4000 VA. It has that capacity to deliver. So now as soon as I tell as unity power factor, okay, so it is basically 4 kVA into the cos theta, which is 1. So it becomes 4000 watts. Output on full load as unity power factor is basically 4000 watts. So the full load current. So at that full load, what will be the current? At that full load, what will be the current?
So 20.
So the full load current is basically this 4000 watts by 200, which is equal to the 20 amperes. So the copper loss at full load. Ultimately, we have to now encounter the losses. Copper loss at full load. What is the meaning of copper loss? I square R. Okay, so you have found out another name of I square R loss is copper loss because the wires are made of copper. So in earlier days, the engineers gave the name as copper loss. Okay. But nowadays, the wires can be made of any other element also. It may be aluminium or any other copper alloy. But this is why, since mostly the wires are made of copper, they give this loss as copper loss because this is the loss, the I square loss that takes place in the wires.
Sir, why do we need to calculate this? Because earlier, what in our experiment of ET lab, what we did is we used the reading of short circuit test to directly put in the copper loss. So
short circuit test may not be the full load condition,
So, but we made sure we use the full load current by varying the resistance percentage.
We were doing the short circuit test at the full load condition only.
Yes, that's what I'm saying.
No, but see, because the load can be something else also. You see, if you read this question, sometimes you may ask, that 50% load, what is the efficiency? Okay, then you will have to basically calculate the loss at that load. You'll have to basically calculate that current, that loss. In fact, it will come out to be the same actually. A load can be full load, a load can be 80% load, a load can be 75% load, a load can be 25% load. So you need to calculate the copper loss at that load. Sometimes in some situation there may be 10% overload. 10% more than the full load also. The equipments are designed to carry a little bit more current also. So in that case, you will have to find out what is the actual loss taking place. So you will have to actually do the I square R. Okay.
Okay, sir.
So the copper loss, so it is simply basically equal to I square R, which is equal to the 60 watts.
Excuse me, sir.
Answer
why we are referring here to low voltage side? We can do the other way also.
We can do the other way also, but you see what is the problem? What is there is something basically given that it is basically a step up transformer.
Sir, why did we not take the current as 19.3 ampere and we took it 20?
Yes, sir.
Which one?
Means we could have subtracted the current going in the shunt branch, 0.7 ampere. And then taken as 19.3 means it will not be more accurate since you have calculated that current.
Yeah, but that is, this is the full load current because this is the current that is delivered to the, it is going to the load. The load is actually taking 20. So the primary current will be, will be higher.
Yes, sir. Okay, sir.
So this is the copper loss. Okay, so the output is delivered is to 4000 watts. So the question is, what is the efficiency? Okay, so efficiency means, what is the definition of efficiency?
Sir, output by input. I mean,
output
power divided by input power.
Output by input. And what is input equal to?
So output plus core losses plus
out plus losses. Output plus all sorts of losses. So one loss we found out is the copper loss. What is the other loss?
It's a core loss.
Core loss. Where will you get the core loss?
Open circuit test.
Core loss is exactly in the open circuit test. The bulk of the losses, or basically the 100% of the loss, is basically the core loss. So the iron, which is also called the iron loss. Okay, so this is equal to 60 watts. So from here you can find out the efficiency equal to output by input, which is output by output plus iron loss plus copper loss, and you can find out this value. Okay. Now the next part of the question is the secondary terminal voltage.
Sorry, but I did not understand the question. That why we are not taking a 19.3 so current.
Where is the 19.3? This is the 20 ampere here. That is passing through this resistance 0.15 and 0.3 J 0.344 ohms. This is the 20 ampere flowing here.
Yes, sir, but 0.7 ampere is also flowing through the parallel branch.
Yeah, but we are only concerned with finding out what is the core loss. Sorry, copper loss.
So for the copper loss, 19.3 ampere is only doing that now. 0.7 ampere is not doing that copper loss, no, sir.
Now, where do you are getting 19.3? This is basically the 20 ampere flowing through at the secondary.
Okay.
So now we get this that
I didn't understand, sir.
So means from the source it is 20.7 ampere coming.
Which one?
Sir, from the source 20.7 is coming.
Now we got this voltage expression.
But sir, 20 ampere is coming from source now.
Which one?
Because here you have 20 ampere current.
Some ampere current is coming from the source, but ultimately the ampere of current that is going to the load is 20 ampere. This is the full load current here.
Sir, out of 20 ampere, 0.7 is going to parallel branch. Then why we are not taking 19.3 ampere?
No, that is actually very negligible, 0.7, 20 ampere is going to the load, and plus 0.7 maybe, and that also not directly addition, All these additions are not directly algebraic additions.
Yes, sir. Yes, sir. Yes, sir. Now
Okay,
I
so if you add them as a phasor, then 0.7 contribution is very negligible. The magnitude will be very close to 20 only.
Sir, the power loss for short circuit test is the copper loss, no?
Power loss?
For the short circuit test, the power reading, that is the copper loss, right?
No, the power loss for the short circuit test is, the copper loss will depend upon the load.
Sir, how did you calculate iron loss, sir?
From the open circuit test, from the low voltage data, it is because it is a fixed quantity. It is
Okay.
not calculated. It is an experimental value given.
Okay, sir.
Sir, won't the copper loss be 21.6 watt? It was given in the short circuit reading.
Hello, sir, you are inaudible.
You're not audible.
So the voltage that is this V2 has to be found out for different power factors. So that is the power factor of unity, the power factor 0.9, 0.8 lagging, 0.8 leading. Okay, so find out the value of V2. So V2 is equal to V1 by A, V1 minus I1 Req cos theta plus Xeq sin theta. Now whether it will be plus or minus, it will depend upon whether it is a leading or lagging load. Whether it is a leading or lagging load, and obviously you see that it has been told that it is the full load current that is flowing. So basically it is the 20 amperes. So from here you find out the terminal voltage at full load at unity power factor. Terminal voltage at full load at unity power factor. So it is given by this. So unity power factor means cos theta equal to 1. So sin theta becomes how much?
0.
0. So you see basically that sin theta component is gone. So V1 is 200 minus I1 Req cos theta is which is 1. So I1 is 20, Req is 0.15. Everything we are doing with respect to the low voltage side divided by 0.5 and you get ultimately this voltage. Similarly, the terminal voltage at full load at 0.8 power factor lag. Obviously, lag is important because the lag will determine whether it will be plus or minus. And then we'll see. What is the value? Anybody got?
So 386.95.
Yeah, it can be there, but my computer is just hanging. Find out for the next part, 0.4, 0.8 lagging, leading. Okay, you got these values?
Yes, sir.
So it have to be very careful when it is the leading load, it is negative. R cos theta minus X sin theta. And it is not that you will have to memorize this, it directly comes from that phasor diagram we just showed. So this is the concept of regulation. Okay. So let us go to the next topic. Transformer efficiency. That is how efficient is the transformer. Okay, can you hear me?
Yes, sir, you're audible.
Yes, sir.
Yeah.
Yes, sir.
So
Yes, sir.
we have been repeatedly studying that there are losses in the transformer. And we have studied at several places. The one of the losses we studied first was the iron loss, which is also called the core loss. The name iron because this is the loss that takes place in the magnetic circuit. It is in the ferromagnetic material. It is also called core loss. And it has got two components. One is the hysteresis loss and the eddy current loss, which we have already discussed in details. Now, both these losses occur in the iron core and are proportional to the maximum value of the flux in the core. That is, it is proportional to maximum value of Bm or phi m. And we saw that the eddy current loss is proportional to Bm square, and the hysteresis loss is proportional to Bm to the power n, where n is Steinmetz constant, whose value varies from 1.5 to 2, roughly close to 2. Because it is actually the area under the hysteresis curve, which is basically a very irregular curve, and finding it under the area under that irregular shape is difficult. So Steinmetz gave an empirical formula. So this node and these two actually contribute to the no load current, which is actually 2 to 5% of the full load current. So when we actually energize the transformer, and the output is open circuited, it only takes the no load current. And if you keep the output open circuited, it is only the no load current that is required to energize the transformer. The magnetic flux flows into the core, and there is some flux linked with the secondary, and it generates an EMF in the secondary. But since that no load is connected, that is, it is open circuited, we only get the no load current flows into the primary. The current in the primary increases as soon as the secondary is connected across some load. The I2 is flown. The I2 opposes the flux to reduce it, and then for that more current I1 comes in, and that is how the transformer operates. This we have studied in details. So this no load current is actually 2 to 5% of the full load current. And we have just seen, we have also done one numerical that these core losses are more or less constant. So whether you operate the transformer at 50% load or 80% load or 100% load, the no load current is fixed, which is 2 to 5% of the full load current. So these core losses are actually taken to be constant. So whatever core losses are there in the open circuit test can also be considered as the fixed core loss of the transformer. And it is basically independent of the load of the transformer. But that I square R loss takes place in the transformer windings. Okay, I square R, that is the actual loss in the resistance, the primary resistance as well as the secondary resistance. And this loss will actually depending upon what is the load in the transformer, what is the current actually flowing. If your current is less, this load is less. If your current is more, this. So this loss is actually a function of the load current. Okay. So the efficiency of a transformer is given by, obviously efficiency is given by output by input. So it is nothing but it is output by input power, which is equal to, so the output power is nothing but input power minus losses. Okay, if your losses are available and input power is available, you can calculate output power. Output power equal to input power plus losses, minus losses. Or if your output power is there and losses are there, then your input power is output power by losses. So that also you can do in the denominator. So this ultimately comes down to 1 minus losses by input power. Okay, so this is efficiency of a transformer. Efficiency is usually denoted by this symbol neta. Okay, all of you know alpha, beta, gamma. So this is the neta, denotes efficiency, which is equal to output by input. And so as I just told, if your output power is known, then your input power is nothing but output power plus losses. So you can, these are basically the different ways of calculating the efficiency. And so if your primary and secondary winding resistances be R1 and R2 respectively, and the turns ratio is A, if you have a turns ratio A and the primary winding is R1, secondary winding resistance be R2, then the equivalent resistance referred to the secondary. Can anyone tell what will be the equivalent resistance referred to the secondary?
R2 A2 by A1 का whole square.
R2?
R2 by A square.
R2 by A square referred to the secondary.
R1 by A square.
R1 by A square.
R1 by A square. So primary, if you refer to the secondary, it will become R1 by A square plus R2.
R1.
Okay.
R1.
So Req becomes R1 by A square plus R2. So if the load voltage is V2 and the power factor be cos theta lagging, you have a load voltage V2, power factor cos theta lagging, and the core loss be PC, which is constant. So output power is how much? Secondary current is I2, load voltage is V2, and the power factor be cos theta. What is the output power?
VI cos.
V2 I2 cos theta. Okay, so from here you can get the value of the expression for the efficiency, which is V2 I2 cos theta, which is output divided by output plus losses, which is V2 I2 cos theta plus PC plus I2 square Req. So here everything is referred to the secondary. Okay. Now, if you divide the numerator and denominator by I2, if you divide the numerator and denominator by I2, you get V2 cos theta by V2 cos theta plus PC by I2 plus I2 Req. So when we were talking of efficiency, what is our objective? What is our desired objective?
To maximize the
Maximize efficiency.
To maximize the efficiency. Now can you tell in this efficiency expression, which one is constant and which one is variable?
Sir, core loss is constant. V2 is variable. Core loss is constant. V2 is variable. I2 is variable.
Any other answer? V2 is variable, but you know V2 that is the voltage at the consumer end. Consumer will obtain at a certain V2. Okay, if you are a domestic consumer, you will always want that at your house the 230 volts is available. You are not going to pay the bill if it is varying too much.
Sir, earlier you said that that load is varying, so V2 will be varying.
V2 is the varying, but it is the job of the supplier, power supply company to maintain the V2.
Sir, here I2 is variable.
I2, that is the current is variable. What else is varies? Theta can also vary.
Yes, sir, theta.
Okay, so
Yes, sir,
theta is the
can
power
vary.
factor angle. What is the desired power factor angle? We are aiming for
So,
what type of power
So
factor?
as close to 1.
Huh?
0.
0 degree.
0.
Angle
So,
needs to be
Power
0.
factor we power
Aiming
factor
for
we
a power
dream of.
factor as nearly equivalent to 1.
so I meant the
Yes.
angle, not the power factor.
Ah.
Hello, sir, you're inaudible.
Yes, sir, you are not audible, sir.
Hello, sir, you're not audible.
There might be network issue.
Okay.
Can you hear me?
Hello.
Yes, and now
Yes,
we
sir.
can hear.
Yes, sir.
Yeah. What is the dream power factor?
So as close to 1 as possible.
Huh?
So
So
1.
Sir, unity power factor.
Yeah. So it is just like your dream CGPA. Okay. 10 out of 10. So it is your dream power factor for the power supply companies to achieve 1. So, but anyway, the customers are actually discouraged to operate at lower power factor. So here the primary variable basically is the current I1. I2, the load current. The primary variable is basically the load current, which will vary widely. Other factors are more or less constant. Okay, so the objective is
Excuse
to
me,
operate.
sir. Why the value of PC or the core loss is constant?
This we have already proved earlier, you know.
So it depends on the hysteresis loop, right?
Uh,
So for different materials, the AV under the loop will be different, right?
But once we have installed the
But,
transformer, you are
Titan,
not going to keep on changing the transformer. Okay.
Okay.
yes, right. Titan, we
Once
use
you
only
have
one
purchased
method.
a transformer, you for your home you are putting some suppose you have a garden or you have to putting some water supply system to that garden and you have purchased a transformer, you are not going to play with it until unless
Right.
it breaks down or something happens. Okay, so it is fixed once you have a transformer. So the objective is to operate to achieve maximum efficiency or efficiency as high as possible. To do that, what you have to do in this expression?
Minimize denominator.
Minimize the denominator. The denominator should be minimized. So for maximizing neta, that is the efficiency, the denominator has to be minimized. Okay, so for maximizing neta, the denominator has to be minimized. So let us do that. So your neta is equal to V2 cos theta by V2 cos theta plus PC by I2 Req. So you see, if you minimize the denominator, you know how to denominate this thing, you minimize, you know better. So if you differentiate with respect to I2, so it becomes, the first part is constant, the second part leads to minus 1, just like 1 by x. So it becomes minus 1 by x square minus PC by I2 square plus Req equal to 0. So from here you see that the transformer will operate at maximum efficiency when your PC, that is the core loss, is basically equal to I2 square Req, that is the copper loss. The transformer will operate at the maximum efficiency when your core loss is actually equal to the copper loss. For that value of I2, where this will be true, for that I2 only the transformer will be at maximum efficiency. And for any other I2, it will not be at maximum efficiency. Okay, so for that I2, this equation is matched. For that I2 where the core loss becomes equal to the copper loss, the efficiency of the transformer, of any transformer, is actually maximum. So the load at which the maximum efficiency occurs, so I2 is nothing but PC by Req, square root of this. So if you divide these both sides, by the full load current. Okay, so the I2 full load, I2 is any current. So for a particular value of I2, the efficiency is maximized, but I2 can be anything. So if you divide this I2 by the full load current, so you basically get I2 by, if you divide by the square of the full load current, so I2 by I2 FL square equal to PC by I2 square FL Req. So this basically, the denominator here on the right hand side basically is full load copper loss, full load I square R loss. So I2 by I2 FL is nothing but PC by, that is the root over of core loss by full load I square R loss, which is equal to a certain M, some constant value. So for M times the full load current, the efficiency is actually maximum. So the efficiency is maximum when the load current is M times I2 FL. The efficiency is maximum when the full load current, when the load current is M into I2 FL. Okay, efficiency is maximum when the load current is M times. So M is given by, M is found out by the core loss is known, which is basically the no load. We can get from the no load test data. You can find out the full load I square R loss. The full load I you can find out from the rating. R you can find out from the given equivalent circuit parameters, or even finding out from the short circuit results, short circuit test data. So then you can find out the full load I square R loss, and you can find out for which value of M this will occur. Okay. Let us do one numerical on this. For doing that, there is some other definition relating to transformer. There is something called all-day efficiency of a transformer. Why this term all-day efficiency? Because a transformer operates throughout the day. When you are drawing power,
and the efficiency varies during the day.
Obviously, because you are taking different amount of power throughout the day. In the morning, yes. When you get up from bed, you take one type of power. When you go to the office or college, one type of power is being used. When you return at the home in the evening, one type of power is used. When you study late into the night, another type of power is used. Okay, so we are using power round the clock. But the transformer is getting loaded different types round the clock. So instead of, this all-day efficiency concept has been coined for the transformer performance. So a transformer is in an electrical distribution system is energized round the clock for 24 hours a day and supplies varying load. If you just think about the load you are consuming in your home, in your hostel, or anywhere, when you come to IIT, you will see that in your hostels, the load consumption is different. In the morning till you leave the hostel, it is one type of load. All the rooms are consuming power. There is power consumption in your dining hall, corridors everywhere. Then as you leave the hall, in one hall, suppose 500 students are going to the institute. then all the rooms are actually switched off. The power consumption in the hostel varies. All the 500 students have left, so only the maybe some.
Here the load refers to the impedance or the current that is drawn.
Current drawn will be dependent on the impedance only.
Yes, sir, but they will be inversely to each other. So that
they are inversely, yeah, but that is how we speak.
Yes, sir.
You can consider your credit loading. Okay, so the more and more subjects you are doing, your credit servicing increases. So that is your load is increased. So, yes, but sir. here your current will increase, your impedance decreases because current and impedance have this reciprocal relationship. So these transformers are subjected to core losses throughout the day, independent of the load. So whether you consume any load or not, whether your LBS hall or MMM hall, whichever hostel you are, whether it is taking any power or not, whether there are 500 borders or 1200 borders, okay, or whether there are no borders all in the class, but at least some core losses are getting lost because the transformer supplying to that hall is energized. It is supplying to maybe the dining hall, the kitchen, the hall office and all. So this transformer is subjected to different types of losses throughout the day, which is independent of the load. So the core loss is basically independent of, but the copper loss, so the I square loss, it be proportional to the square of the current. It actually varies with load. So a transformer basically is subjected to different types of load at different hours. Okay. So in order to access the performance of such a transformer, an all-day efficiency is also known as the operational efficiency is computed. And this all-day efficiency is defined as the So you see that this all-day efficiency, this is actually defined with respect to the energy consumed. In earlier case, you saw that the efficiency was defined with respect to the power. Okay, the output power by input power. So output power by output power plus the loss power. But this all-day efficiency is actually is defined with respect by the energy consumed. So energy is basically power into time. So in the numerator, you have the energy output in kilowatt hours for 24 hours. So throughout the 24 hours, how much kilowatt hour is output by the transformer? And in the denominator is how much kilowatt hour goes as input to the transformer. So you see it is defined with respect to energy. So higher all-day efficiency, it can be achieved by minimizing the core losses. Okay, by minimizing the losses, only it can be achieved. If somehow you can minimize these losses, you can achieve higher and higher all-day efficiency. So minimization of core losses, we saw that core loss is proportional to, because you don't have any control over the load. You don't have any control over the load. You don't have any control over the customer behavior. You don't have any control. When the students are back in the hostel, there is no control. What type of consumption the students will do. Somebody will just, switch on some light and fan. Somebody will have some computer or laptop. Somebody will have some, Walkman or something. So, okay, so that is the load behavior over which the power companies don't have much control. They can only have control over, some infrastructure. So if they can use some transformers which has low core losses, then at least they can try to maximize this all-day efficiency. And that can be achieved if there's by special design, in the design stage, by using a good some grades of steel in the core, or by operating the transformers at low flux densities, because we saw that these losses depends on the flux density. So let us
we will not consider the power loss in the denominator, like we did in the previous case. We'll only consider the core loss.
Here everything is defined with respect to energy. Even if it is core loss, it is the energy of energy loss due to that core loss. The core loss takes place over a particular duration, and in this case, it is basically 24 hours. So if you can,
Yes,
by achieving some improved design, if you can reduce the core loss, that is going to have effect on the alt efficiency.
Okay, sir.
Because you don't have control over the load. Let us do one problem. So a transformer has its maximum efficiency at 0.98, on efficiency of 0.98 at 15 kV at unity power factor. On a particular day, its load, what is this? For a particular day, it is having such a load that 2 kilowatt at power factor 0.5, it is for 10 hours. For 10 hours, this is how the loading took place over the 24 hours. For 10 hours, it was 2 kilowatt at 0.5 at power factor 0.5. For 8 hours, it was 12 kilowatt at power factor 0.8, and for 6 hours, rest of the 6 hours, it was 18 kilowatt at 0.9 power factor. Find its alt efficiency. Okay. So you see, it is having there is some clue hidden in this problem. It has a maximum efficiency of 0.98 at 15 kV at UP at unity power factor. So what is the output at unity power factor?
15 kVA.
15 kVA. So the output at unity power factor is 15 kilowatt, not kVA. Whenever we talk of output, it is in power, watt.
Yes, sir.
15 kVA into 1. As soon as you multiply the kVA with the power factor, it becomes watt. Okay. Now you are given the efficiency. What can you find out from here?
Core loss and
Find out. So you are given the eta max. So maximum efficiency is 0.98. So at eta max and at UPF, your input is equal to output by eta max. And which is basically equal to 15 by 0.98. What is the value?
15.306.
15.306.
So you see, this is the input, and you already know the output. So what is the meaning of this? Input minus output?
Losses.
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 But this is what are these losses?
Core loss and
Core loss and copper loss.
Core loss and copper loss.
Yes,
And
sir.
this is maximum efficiency condition. So what is the relation?
Both will be equal.
Both are equal.
Both are equal.
Both are
Okay,
equal.
So at maximum efficiency, your iron loss is equal to the core I square R loss. So you can find out each of them. Each of them is just half.
0.153, so
0.153.
Okay, because we are using the maximum efficiency condition. So this is the core loss. Now we are talking of alt efficiency. So what is the energy lost due to the core loss in 24 hours?
0.153 into 24.
multiplied by 24.
So we will get the kilowatt hour. Okay, so since the energy loss due to the iron loss in 24 hours, you get this, because this will be required in your energy calculation. Okay, so this is the energy loss due to the core loss in 24 hours. Now that is hourly variation of the load. For 10 hours, it was a certain kilowatt. 12 for 8 hours, it was a certain kilowatt. For 18 hours, for 6 hours, it was a certain kilowatt. So so you have to basically calculate the different energies that was consumed by the load. So your hourly consumptions are given. So from that you will get the total energy consumption for 24 hours. So you are basically given this.
Yes, sir.
For 10 hours it is 2 kilowatt at power factor 0.5. For 8 hours it is 12 kilowatt at power factor 0.8.
Sir, what is the use of power factor given here?
Huh?
Like we can do 2 into 10, right?
2
into 10 plus 12 into 8 plus 18 into 6. Power factor, like what is the use of power factor here?
No, this is basically the load. You'll have to find out what is the loss also. The I square R loss.
Yeah, sorry. Yeah.
This is the total power that you are enjoying. That is fine. Okay. As Soham told, so 2 kilowatt for 10 hours. So that is the power output power you are getting. 12 kilowatt for 8 hours. That is also the output power output energy you are getting.
Sir, in all these cases, because sir, in all these cases, we will have to find different copper losses, na?
Yes.
Because we now have iron loss and we can subtract it from the total loss.
Iron loss we have found out. For 24 hours, whatever the energy consumed by the iron loss, we have already got.
Yes.
Okay, but for this different time duration, your currents are different. And once your currents are different, you'll basically have to find out the this thing. You have to find out the different types of iron loss, the energy consumed due to the iron loss, copper losses. So the rated output at the given power factor. So the rated output at given power factor. So for the first case, the power factor is 0.5, and it is 15 kVA. So the rated output is 7.5 kilowatt. The transformer is giving the output to the loads. So for a particular output, for a particular power factor, what is the rated output? Similarly, for the second case, when the power factor is 0.8, it is provided a 0.8 load is supplied by a transformer of 15 kVA. The rated output is basically the 12 kVA, 15 into 0.8 kilowatt. Similarly, for the third case, it is basically 18 into 0.9, that is 13.5 kilowatt. 13.5. 13.5.
Sir, why are you multiplying with the power factor?
To get kilowatt, because this is a transformer which is supplying different loads. Sometimes 0.5, sometimes 0.8, sometimes 0.9. So what is the power it is supplying? kVA into power factor. So that is the rated output.
Sir, 2 kilowatt, 12 kilowatt, these are input or output?
This is the load. That is the load connected at the terminals of the transformer.
Okay, sir. Okay.
So, sir, it is the magnitude of total power, like reactive and non-reactive power.
We are only talking of the the active power only, kilowatt.
So, when we multiply it by power factor, then we are getting the active power, na?
Then we are getting active power.
Yes, sir.
Now, the I square R loss at the given power factor. The I square R loss at the given power factor. Okay, so the I square R loss at the given power factor is basically this 2.
So in the last column, there should be 15 into 0.9 in the rated output.
Yes, sir.
Here.
This one?
Yes, sir. Actually, there should be 15 instead of 18. Actually, you have written correct 13.5. But
just a typo, right?
Yes,
Which one is wrong?
So 18 instead of 18.
Sir,
there should be 15.
Place of 18. Yes, sir.
Yes, sir. Yes, sir. That also I was thinking.
Which one is wrong?
Sir, in the last
rated
column
output,
below, we got 18 at 0.9. It should be 15 into 0.9 to give 13.5 because 18 into 0.9 is around 16.2.
Oh, yes, yes. The transformer. Okay, I'll correct it later. Or maybe I'll correct it, yes.
Okay, sir.
The transformer rating is 15 only, yes. How, it cannot be 18.
Sir, screen is not visible.
Visible?
Yes, sir.
Yes, sir. It's visible.
Okay. So the I square R loss at the given power factor. At the given power factor, you have to now find out the I square R loss. We already found out the I square R loss for the maximum efficiency condition. So the derivation that we did earlier, using this 2 by 7.5, this 2 by 7.5 whole square multiplied by 0.153. So this is how you compute the I square R loss. So for each of the different loads. And once you have got the I square R loss, you can find out the energy loss, just multiplying it by this time. Okay, so but just multiplying it with this 0.0109 into 10. Similarly, 0.153 into 8. Similarly, 0.272 into 6. The energy lost.
So can you explain I square R loss step once? What are we
Which
doing
one?
there?
Can you explain
How
again?
2 by 7.5?
It is just the application of the formula that we derived last just before the example to find out that M.
So M we derived with respect to I, no? I2 equal to M of I2 FL. So here we are doing this with respect to power. So I mean, how are we doing that?
No, earlier it was that I square R loss, full load I square R loss.
Acha, okay, we are we are doing M square right here.
Yes.
So can you explain once again I square R loss, sir? How did you calculate it?
You have to find out the M.
Oh, yes, sir. Yes.
Okay, and ultimately the energy output is already very easy. It could have been done this 2 into 10, 12 into 8, 6 into 18 into 6 in kilowatt hour. So from here you can get all the efficiency. The total energy output during the day is basically 20 plus 96 plus 108, total energy output. So all the efficiency is output by input. So it is output by output plus losses. So energy due to the I square R loss. So this summation, this much kilowatt hour. Energy loss due to the core loss is already found out. So the total all the efficiency is basically this 224, that is the total output energy divided by 224 plus this 3.672. It comes from the core loss, that is the iron loss, and 2.965 it comes from the I square R loss. That is every energy. Everything is in energy. Okay. So everything is in energy. And you see that the all-day efficiency is 0.9712. So you see your all-day efficiency, earlier we got, it was given the maximum efficiency. So maximum efficiency occurs at a particular condition when your core loss is equal to the iron loss. But throughout the day, in 24 hours, different types of situations will happen in the transformer. And it will be at very few occasions the core loss will be equal to the iron loss. So you see that your all-day efficiency is actually less than the maximum efficiency. Okay. Okay.
Yes, sir.
Yes, sir.
Yes, sir.
So this is the concept of efficiency and all-day efficiency for the transformer, and we have actually just completed numericals also. So we will study another important concept in a transformer, which is known as auto transformer. Auto transformer is actually a device which you must have used in the laboratory. Though we are doing it in the virtual mode, but it is actually, if you had done the labs offline, you would have actually handled auto transformers by this time.
Yes.
Okay. So a auto transformer, it is actually a simplified form of a transformer. It has basically got a single winding. You don't have, the two windings just like the normal transformer. In normal transformer, you have a primary winding and the secondary winding. So here you have a single winding where part of the winding is used as the primary and a part of the winding is used as a secondary circuit. And that is how you make the transformer. The input and output are electrically connected, since it is basically the same winding that is being used. Part of the winding is used as the electrical, as the primary, part as the secondary. So there is actual electrical connection between the primary and the secondary. In a two-winding transformer, in the other transformer that we have studied, there is a primary and secondary which are not electrically connected. They are magnetically coupled. Okay, so those type of transformers are actually called two-winding transformer because there are actually two windings. But this is a transformer where a single winding is basically, part of the winding is used as primary, part of the winding is used as secondary. So since a single winding exists there, both the windings have actually electrical connection. So both the currents, whatever the flux basically is generated by both the windings, by the single winding only, and they get superimposed in the common part of the winding. So your auto transformer actually looks like this. There is a single winding. You can see this?
Yes, sir.
So
Yes, sir.
AB is the full coil. Okay, the one single winding. And from the point C, so your BC basically acts as the secondary coil. So for certain point C, there is a tapping. And this BC uses the secondary, and from there the voltage V2 is generated, the secondary voltage, which is going to the load. So you see your input voltage is V1 and the output or the load voltage is V2. So if your input current is I1 in the direction shown, and there is the out I2 is the load current. So you see in that segment BC, the current should be I2 minus I1 in this. If it is in this direction, the current is I2 minus I1. Then only at C, if you apply KCL, there will be I2 going out. Okay. Clear?
Sir, I have a doubt. So instead of this, why can't we use directly a potentiometer and use the jockey to do the same tapping? Like, why are we using
Yes.
transformer? Yes,
Same question.
I had.
Sir, you are not audible.
Sir, you are not audible, sir.
No, here we have iron. It is not just a.
That you are not audible.
Can you hear me?
Yes, sir.
Yes, sir. Now we can hear you.
Yes, sir.
Yes, sir.
So this is the difference between this potentiometer and this auto transformer, because
Sir,
it is
we couldn't
basically.
hear anything you said.
Actually, we didn't hear anything. Because
So
we were
here
not-
basically there is a ferromagnetic core. The winding is wound over a ferromagnetic core, and the full of the winding is used as one one coil, and part of the winding is used as the other. Because the transformer effect has to be there. It is not just a coil, but it is not only doing voltage division, but there is a transformer effect.
Means it increases the voltage also, which is not done by the potential.
Yeah,
but then,
there will be increase. We will actually do a numerical where I will show that there is an increase also. That will be at the end. You have to wait till that example. We'll actually do one mathematical example, one numerical on auto transformer also.
So in this auto transformer, V2 can be greater than V1?
It can be possible. We will actually do that one example of that type. I found one example and I put it in the slide. It will be maybe in the 2 slides side. So you see that AB with the total primary turns N1 is tapped at any convenient point C. A number of secondary turns C to B is basically N2. The supply voltage is V1 and which is applied across AB, and the load is connected across CB, which is with the voltage V2. Okay. So this is basically the principle of auto transformer. We'll do now some. So you see here also we will find that basically the transformer voltage ratio equation holds. That is V1 by V2 is equal to actually N1 by N2 is equal to the turns ratio A. Okay, suppose the primary voltage is V1, the secondary voltage which is across the load is V2, and the number of primary turns is N1 and the secondary turns is N2, N1 by N2. Similarly, what actually happens here is the same MMF balance equation also holds. So MMFs of the two windings actually balance each other. What are the two windings? What is the first winding? The primary?
AC.
Who told AC? Primary winding. Which one is the primary voltage?
V1.
AB is the primary winding.
Yes.
In the primary winding, how many turns?
N1.
N1. What is the primary current?
I1.
I1. Similarly, what is the secondary?
V2.
N2 and I2.
N2.
No. What is the second winding you call the secondary here?
CV.
BC. Okay. In BC, how many turns?
So N1 minus
N2.
In BC, how many turns? I have already given it in the description.
N2.
N2, sir. N2, sir.
Sir, your voice is breaking a lot.
Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Voice is breaking.
Yes, sir. Yes, sir.
Yeah, can you hear me?
Yes, sir.
Yes, sir.
Yes,
Now you're
sir.
audible.
Yes, sir.
In BC, what is the current? BC, what is the
I2
current?
minus I1.
Sir, I2 minus I1.
And number of turns?
I2 minus I1 and N2.
N2. So what is the MMF balance equation?
Sir, N2 into I2
I2
minus
minus
I1
I1.
into N1 minus N2 into I1.
I1. Okay. So from here you will get certain relation. I1 N1 equal to N2 equal to A, that whatever type of relation we got earlier. So the power that is transferred inductively, the power that is transferred inductively by transformer action, that is across the load, which is basically V2 into I2 minus I1. And from here you can get A minus 1 by A V2 I2 using all these relations. So today we will go a little bit more than 5 p.m. because that I want to complete that this thing auto transformer numerical also. Very interesting numerical I found, and which you'll find it interesting. So power transferred by the inductive action is basically this. Now we find out the weight of a transformer. Suppose we compare the weight of a transformer. So the weight of a conductor is actually proportional to the product of the current and the number of turns. If you find if you compute, so the weight of a conductor is basically proportional to its volume, L into A. Okay, so and ultimately if you relate it to the current, you will find that that L in this case of a transformer, it is L. L will be proportional to the length, will be proportional to the number of turns. Okay, the length will be proportional to the number of turns, and this area will be proportional to the current. Okay, because the larger the area, smaller is the resistance and larger is the current. Okay, so the weight of the conductor is basically proportional to the product of the current and the number of turns. So if we try to make a comparison between a two-winding transformer and then the auto transformer of the same capacity, that is, we want to make a comparison between the weight of a two-winding transformer and an auto transformer of the same input-output specification, same type of voltage ratio relationship, same core flux, okay, same core flux density Bm, phi m, and same current density. There is another term called current density. That means amperes per meter square in the conductors. So if you're comparing the two-winding transformer of the same input-output specification, same core flux and same current density, then WAT by WT. WAT means auto transformer. So WAT is the auto transformer, that is basically equal to the the AC part. The current is I1 and the number of turns is N1 minus N2, plus the BC part, the current is I2 minus I1 and the number of turns is N2. So that is proportional to the weight of the auto transformer. Similarly, for the transformer, in the primary N1 turns plus I2 into N2 turns in the secondary.
Sir, your voice is breaking, sir.
Voice is breaking.
You can see my slide.
Yes, sir.
Yes, sir.
Yeah. So if you compute this, in a two-winding transformer, I1 N1 equal to I2 N2. So in the denominator basically becomes 2 I2 N2. Okay. Similarly, if you the numerator is basically 2 I2 minus I1 into N2.
Sir, here weight of conductor is actually mass of conductor.
Yes, weight means mass.
Okay.
Mass of the conductor, because we are trying to compare a two-winding transformer and an auto transformer, but which have the same input-output voltage, input-output specification, same core flux, same current density. So from here you will get, so this is equal to 1 minus I1 by I2.
Sir.
Will be equal to I1 and into number of turns. That is current into number of turns.
This is minus, so it is 1 minus 1 by A. So 1 by A has some value. So 1 minus 1 by A is a value which is less than 1. So you see the weight of the auto transformer for the same input-output specification is going to be less than a normal two-winding transformer. Because the right-hand side value is less than 1. So for the same input-output specification, same core flux and current density, the auto transformer weight is going to be less than a two-winding transformer.
Sir, sir, how can you say that weight of conductor will be product of current and turns?
What was
Sir,
the
you are
question?
not audible, sir.
What is the question?
Sir, how can you say that weight of conductor will be product of current and turns, number of turns?
You find out weight is volume into density. Volume is what? L into A. Okay, length of the conductor into A. Length is proportional to the number of turns. Okay, and area, if you increase the area, what will happen to the resistance?
Resistance will decrease.
Resistance will decrease, current will increase. Okay.
Yes, sir.
So area increase means current increase.
So but distance also depends on length.
Weight is proportional to
Sir, you are not audible, sir.
Sir, you are not audible.
Okay, can you see the slide?
Yes, sir. Yes.
Yeah, so this is how we can show that an auto transformer is lower in weight
Sir.
than a 2N in.
Sir, I was saying that resistance is directly proportional to length, so current would be inversely proportional to length. So why aren't we considering that? Why are we considering only area? Like if length increases, turns also increases, but current also decreases, right?
Current also decreases.
Yeah, so why aren't we considering that?
No, eventually there is a, the area is also dominant. The area, the cross-sectional area is in the denominator. It influences the resistance value more. The cross-sectional area. Okay. Can you hear?
Yes, sir, you're audible.
So it is more sensitive to the cross-sectional area.
Okay, sir.
So similarly, I square loss, R loss of an auto transformer is lower than a two-winding transformer. These are some of the characteristics. Efficiency of an auto transformer is higher than a two-winding transformer. Efficiency wise also it is higher because we have got rid of one coil. There may be very few leakage flux.
Sir, you are not audible, sir.
You are not audible.
Sir, you are not audible again.
Transformers, since many.
Sir, you are not audible.
Can you hear?
Yes, sir.
So auto transformers are mainly used for interconnecting systems that are operating at roughly the same voltage. And if you were here, there was an experiment on induction motors. Induction motors, ironically, because of loss of time, we could not, because of less time, we could not do over the, all the sections. So they are also in the starting. For starting the motors, in every motor as a starter, there the auto transformer starting is there. Typically, if you have seen your labs, the auto transformers will actually look like this. Okay, and you see there is some arrow, and where it can be, the varied from 0 to 100%. Okay, the secondary voltage can be 0% of the primary, or it can be varied to some value, 30%, 40%, 50%, and to 100% of the primary. So this is how the auto transformer is. So by just rotating by this hand control, you'll have actually control over the this spool type arrangement at the top of the auto transformer, by which if you change, the voltage will change. In many of your experimental setups, you have been told that vary the voltage and take the readings at this voltage, isn't it? You have done in your lab. Have you done in your lab where instruction is to vary the voltage?
Yes, sir. Yes, sir.
So in the virtual lab, it is through some code, through the slider, you could have varied the voltage. But in the actual lab, you will have to actually operate an auto transformer. You have to use your hand and rotate this.
Sir, you are not audible.
I cannot see the slide.
Yes, sir, you are not audible.
Can you hear me?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Screen is visible?
No, sir.
No, sir.
No, sir.
No, sir.
Mm. Now?
Yes, sir.
Yes, sir.
Yeah, so we will do the example on auto transformer. So it is given that, can you see the problem?
Yes.
Yes, sir.
Yes, sir.
Given that you are given a two-winding transformer. You are given a two-winding transformer, 200 volts, 400 volts, 10 kVA, 50 hertz single phase transformer that has a core loss 75 watts and a full load copper loss of 150 watts. So calculate the efficiency of the transformer at full load of 0.8 power factor. So that is the first part of the question. So first part of the question is with respect to a two-winding transformer. But the second part of the question is the transformer is now connected as an auto transformer. The transformer is connected as an auto transformer to give 400 volts, 400 by 600 volts. So what you do is that one coil you take and put in the top of the other to make the auto transformer. Calculate the kVA rating and efficiency at full load of 0.8 power factor. It's a nice problem. In the same problem, you are getting tested for a transformer, two-winding transformer concepts as well as for the auto transformer principle. All of you can see?
Yes, sir.
Yes, sir.
Yeah. So
Yes,
for the two-winding transformer, the power output, because you are asked to calculate the efficiency at full load at 0.8 power factor. So you are given 100 kVA. So the power output is not very simple. 10 kVA, 10 into 0.8, which is equal to 80 kilowatt. That is the output power. And calculating the efficiency. Efficiency is output by input. And you are also given the core loss. You are also given the full load copper loss. Very simple to calculate the efficiency. You can find out. Find out the efficiency.
So 10 kVA is given at unity. So 10 kVA is given at unity power factor.
Where is unity there? You have to read what is there in the problem. Anywhere unity is written?
No, sir. I'm asking that how you have calculated power output 10 into 0.8?
What is the power factor given? Part A of the question.
.8.
Power factor I have given. Where have I given unity power factor? So what is the efficiency? Anybody found out? Who has found the efficiency?
0.9726.
Something will get. So your losses is basically 75, which is the core loss plus 150 watts is basically the full load copper loss. That is 225 watts. So the efficiency is 8 by 8 plus 0.225. We have 225. We have converted to kilowatts, and ultimately you get this efficiency. You got this?
Yes, sir.
Yes, sir.
So now come to the second part of the question, which is actually interesting. That is, this two-winding transformer is actually converted to an auto transformer. So this two-winding transformer is actually converted to an auto transformer, such that for the auto transformer, the primary voltage is 400 and the secondary is 600. So if you see your two-winding transformer is 200, 400, 200 by 400. So if you put that primary over the secondary and take the output from the secondary, both together, then you get the 600 volts. And you feed the input to the 400 volts. Okay, so basically have a circuit like this. A two-winding transformer is basically two coils. So this one coil, which was the 200, you take it up and put over the 400 volts. So, and if you take this to output, the output is basically 600. And you feed the input as 400. Is okay? All of you can see this?
Yes, sir.
Yes, sir.
Okay, so though the coils are looking identical, but they are actually having different turns. Okay, so now this is the auto transformer, and if there is a current I1 here, and then there is a current I2 here. Okay, so what is the current in this coil, in the lower coil?
I1 minus I2, sir.
I1 minus I2.
I1 minus I2 in this direction. It will be I1 minus I2 in this direction.
Downward.
Downward.
Yes, sir.
Okay. Now tell me, what will be the value of the current I2? What will be the value of the current I2? Because I2 is the current that is coming out of this 200 volts original coil that was in the primary. This 200 volts, this segment of the coil, it was earlier part of the primary of the two-winding transformer. Okay, and it was rated for how much kVA? The 200 volts, this top coil was rated for how much kVA?
10
kVA. So what will be I2? So what will be I2? 50. So I2 will be basically equal to 10 kVA, that is 10 into 1000 volt amperes divided by 20 equal to 50 amperes. Because it was part of the original two-winding transformer of 200 volts and 10 kVA level. Similarly, what is I1?
So 25.
So what is I1 will be, I1 will be known from, because see this coil, the lower coil, the voltage across the lower coil is 400. And it was part, huh? The lower coil is voltage is 400 and it was originally part of the two winding transformer with kVA rating 10 kVA. Okay, so from there you have to first find out I1 minus I2. So I1 minus I2 equal to, following the same approach, I1 minus
25.
equal to 25 ampere. So now you can find out I1. I1 equal to
75.
75 ampere.
75.
Equal to 75 ampere. So now you see, so this is the auto transformer where we have which has been converted from a two winding transformer when we have found out the primary currents and secondary current of the auto transformer. And this is an auto transformer whose primary voltage is 400 and secondary voltage is 600. Okay. And in the secondary, the voltage is 600 and it is also delivering 50 ampere. So what is the kVA rating of the auto transformer? kVA rating of the auto transformer?
30 kilowatt ampere.
30 kilowatt ampere. So whether you consider the primary or the secondary, so in the secondary it is 600 into 50 is equal to 30 kilovolt, 30 kVA. Similarly, if you take the primary, there also you will get 30 kVA.
75
into 400. So kVA rating equal to this. So what we see, that using a two winding transformer of 10 kVA, we have achieved an auto transformer of 30 kVA. A powerful auto transformer. It has more power handling capacity. Okay, so we have basically designed a auto transformer using a two winding transformer, but the power has increased compared to the parent two winding transformer, power handling capacity. So the power output, if it is 30 kVA and it is telling that the full load power factor is at 0.8 power factor, the power output is this. Okay. You can hear?
Yes,
Yes,
sir.
sir. Yes.
So you see,
Yes, sir.
the next part of the question is the efficiency. So the efficiency is equal to 24, which is the output, by 24 plus the losses, is equal to 99.07%. So you see that efficiency wise also, we have achieved a transformer action which is more efficient than the two winding transformer. And power also has increased.
Sir.
Hmm.
Sir, when we convert this two winding transformer to an auto transformer, we'll change the structure of the core, right, to make it a single coil. So will the core losses remain the same?
See, we will not change the structure of the core. Like for this example, suppose already there is a two winding transformer, there are two separate coils. Okay.
Yes.
So, then you join the coils. Basically in an auto transformer, there is physical connection between the coils. So basically you have to establish connection between the coils. Okay, without changing the core. It is very difficult to change the core because there is a heavy core is there. What you do is you will just play with the winding connections. Is it clear?
Yes.
Yes, sir. Yes, I got it.
When you just imagine what is the or should I draw?
Yes, drawing would be better.
Okay, I'm trying to use my whiteboard. I see whether I can do it. Yeah, okay.
Sir, if an auto transformer has so many advantages, why do we still continue to use two winding transformers?
So many?
Like auto transformers have a lot of advantages, right? Its weight is less and the power rating
No,
is high.
they are also used, but anyway, it will lead to a complicated connection also.
Achha, okay.
But it depends upon the application where they are required and all. Say if you have
Maybe
a
it's more costly.
Yeah, it will be
than
costly.
normal ones. Yeah.
And it has a rotating thing. So there is the pointer which is rubbing on the coils. So this is our transformer. All of you can see?
Yes.
Yes, sir.
So now we have to make some sort of a suppose this is this V1 and somehow we now need to connect these 2 points. We connect these 2 points and from here we take the output. So the output is across these two. Clear?
Yes, sir.
So basically it will be some sort of a circuit change you have to do. Because this is once you have purchased a 2-winding transformer, you have purchased everything. You have purchased the core, and over the core the windings are there, only the terminals are coming out. Okay, only the terminals, these terminals are available. So only once the terminals are available, then we have to make some other circuitry to achieve the auto transformer. Okay? Does it answer your question, Soham?
Yes, sir, I got it. So like I was thinking from the diagram you showed earlier, I was thinking it has to be a code like a circular code. This is a square code, so it can be a circular. I was thinking like that, so that's why I said that.
No, those circular core and all that we put it nicely to explain in the class. But in actual design, for reason I told all of you to see your locality, you must have seen a pole mounted transformer where inside basically is you have this type of rectangular core. But circular core is also there. If all of you search in the auto transformer action because ultimately there has to be a circular motion. That transformer that I showed there, the variac, there is a rotation. So there the coil is actually in the form of a toroid. Okay, so there the coil is actually in the form of a toroid, and there is coil and coiling and so on. Can you see my this thing? Figure is not so nice, but
Yes, sir.
something is
Showing.
there, and something is some other internal tapping is there.
Sir, share an image on the chat.
Huh?
I shared an image
Yes.
on the chat of the
Yeah,
toroid.
many images are there. If you search in the Google, you can get even better images actually. Even when you come here, in the lab you may find some variac which is opened up. There you will get better images. Okay. So that is all for today, and that is all about the course. There is a small element of safety, electrical safety. Okay, we decided that we teach electrical safety also in this course, but because of this time we cannot give a lecture. I have got a PDF file. I think I can mail it to all of you on the safety, electrical safety. Okay, Professor.
How long is it?
I have it is some 8-10 pages long. The electrical profile on there is a lot of material even in the net and all on safety, but the Professor Kishore circulated that file. I think I can directly mail you that file.
So is that part of the syllabus for exam?
Officially, it is part of the syllabus.
Okay, okay.
So, but we are not even in the lab.
Yes, sir. Please send us.
We are not even in the labs. We are studying online, sir.
That is okay, but it is better to go through them so that whenever you actually do the labs, all these things should be at the back of your mind. So you are right now only doing the theory, but theory is also required, so that when you actually do experiments or you have to do actual circuits or some precaution you have to take, then suddenly you will remember, oh, I have read this thing in the theory.
Sir, what is the syllabus for last test?
Module 4. So, thank you all of you.